In this last video, we are going to take a look at some of the most common types of fragmentation patterns. So just a quick review, when that molecular ion, that unstable molecular ion gets formed in mass spec, it's not, as I said, it's not very stable and it will fragment to become more stable. And compounds typically fragment in a variety of patterns, and those patterns are few and far between, especially within functional groups. So I'm going to look at a few different types of functional groups and some of the most common types of fragmentations associated with them. And again, the goal of mass spec interpretation is not to identify every single signal that you see here. That's impractical and it just doesn't get you anywhere. But you should be able to kind of tell where what the major fragments are, at least the biggest, the where the molecular ion is, and at least what the base peak represents. What is that the fragment of the base peak? So when it comes to alkanes, we'll start off simple and just kind of look at uh, unbranched alkanes. And one of the most common types of fragmentation patterns is once the molecular ion is formed. So that's here at about 86. There's our molecular ion. Okay, and that's that radical cation that gets formed after an electron is ejected. And one of the most common things we do with an alkane is just start lopping off carbons. Start at the end and break off a carbon. Right? So we'll end up with 1, 2, 3, 4, 5, this cation and a radical, um, a methyl radical. Now, again, we don't see radicals, we see cations, anything with a plus charge. And if I take off a methyl group, what have I subtracted? I've subtracted a mass of 15. And so this signal right here at 71 is that cation, because 86 minus 71 is a mass of 15. Now, if I look at going from this to my base peak, the base peak has a mass of 57. Well, what is the difference between 57 and 71? That's a loss of 14. So we'll start with this ion here and lop off a CH2, which has a mass of 14. So this base peak here has that represents that radical. I'm sorry, not radical, that cation. And most likely it'll fragment to form the more stable, like secondary cation, but it's okay if you just want to put the positive charge outside on the brackets. And then we keep on going down here. We go to the next largest peak. That's at 43. Well, what's the difference between 43 and 57? That's a loss of a mass unit of 14. So again, all we're doing here is lopping off another carbon, and that gets to this cation. And then if we go on one more here, that is 29. Again, what is the difference between 29 and 43? That's another loss of 14. So hopefully you're kind of picking up on the pattern. All we're doing is just taking off one carbon at a time, and that gets us to our next cation. And that's pretty much it for like unbranched alkanes. You just kind of lopping off a single carbon at a time. Now, if they're branched, you'll see that same kind of instance here. But with branched alkanes, the major fragments tend to be the ones that would form like more stable carbocations. So our molecular ion is here at 72. That's the mass of isopentane. So that's that radical cation. Once it gets hit by an electron, it becomes a radical cation. Notice it's not as abundant as the others, and that's normal. Sometimes it's very hard to find the molecular ion. It just depends on how stable it is. Now, what I want to take a look at is with this branched alkane, if I were going to break apart a bond, to get a stable carbocation, where would I do that? If I blow apart the molecule at this right here and imagine forming this cation and then this ethyl radical. Of course, I don't see the radical, so I don't really care much about it. Actually, I'll draw it this way so there's no confusion. So the molecule fragments there, and I get that secondary carbocation, and this has a mass of 43. Okay, so my fragment here at 43 is most likely this cation. Now let's take a look and, that's our base peak. Let's look at this difference here between 72 and this here, which is 57. Now, again, that's a loss of 15. Okay, so a loss of 15 always or usually means methyl group because that has a mass of 15. But which one do you think am I gonna break apart? Should I break apart this one to get this cation, or should I break apart this one to get this cation? So the only stable cation that I could probably make is here, secondary. All these here are primary. Okay, especially if it's going to come off, if it comes off this end here, this carbon is a primary carbon versus this one ends up being a secondary carbon. So the most likely fragment for 57 is just this butyl chain. So that's the only thing, extra thing you have to take into consideration with branched alkanes is that it will fragment to form with a more stable carbocation, and those will be your major fragments. All right, let's take a look at ketones. You can also apply this to aldehydes as well. But ketones will fragment in two very common ways. They will usually fragment in something called alpha cleavage, where you will break one bond around the carbonyl or the other bond around the carbonyl. So if I break off that first carbon, so if we look at what would happen if I did the blue pathway, I would get a methyl radical, which we don't see. And then we would get this cation. And if I just quickly added up the masses of all of that, that would be a mass of 85. Now, if I fragment the other way, I would get this butyl radical, which again, we don't observe. And the one we do observe is this cation, and that has a mass of 43. Let's take a look at our mass spec here. Notice my base peak is right there at 43. That represents this cation from the alpha cleavage of the ketone. And I also see a small one of this cation at 85. Now this one here forgot to address this at 100. That is our molecular ion. So that's the whole ketone minus an electron, so it's a radical cation. Now, there's one other major peak here, and this is another common type of fragmentation that occurs in aldehydes and ketones called the McLafferty rearrangement. And so I'm going to take the molecular ion, and I'm just rotating a bond around. I haven't changed it at all. This is our molecular ion. And I just took a bond and I rotated it. And if there is a carbon um, 3 carbons away from the carbonyl, so 1, 2, 3, we're going to do this kind of McLafferty rearrangement. So follow this along with this mechanism. So we use those pi electrons to pick up that hydrogen. This forms a double bond here, and this forms a double bond here. Now, the fragment we care about is this radical cation that gets formed by the McLafferty rearrangement. Notice what happens to carbons 2 and 3 and the other one attached to it. It's just, it comes off as a radical, so we don't care. But if we take the mass of this, that's a mass of 58, which is our next highest abundant peak. So those are the two main types of fragmentation patterns I want you to know for aldehydes and ketones. Is you'll do an alpha cleavage around the carbonyl. So getting a cation on either side is possible. And then the other major one that you should know is the McLafferty rearrangement. All right, let's take a look at alcohols. So here's one butanol. Oh, needs one more carbon. And here's a case of where the molecular ion is barely distinguishable, right there at about 74. And again, kind of like aldehydes and ketones, alcohols have two main types of fragmentation. The first one is the loss of water. Okay, water has a mass of 18. And so notice here between the molecular ion and the first fragment, actually, I'll go the other way. That's a loss of 18. We're going from 74 down to 56. So I'm going to take my molecular ion and I'm getting rid of a hydrogen and an OH to get this cation. Now, another common type of fragmentation, like ketones and aldehydes, is alpha cleavage. So again, I'm going to um, break that, and I could end up with, oops, sorry about that. I could end up with this cation in this radical, which I don't care about, or I could end up with this radical, which again, I don't care about, and this cation. So this has a mass of 43. This cation has a mass of 31. And if you kind of see what my next biggest peaks are, I do have a signal here at 43. which represents the alpha cleavage in that form. And then at 31, I have this cation from the other um, alpha cleavage. And then finally, let's take a look at aromatic fragmentation. These are actually pretty simple. So again, aromatics, that is the kind of common term we give for these compounds that have these benzene structures in them. We'll go a lot deeper at the very end of the semester about how we talk about aromatic compounds. And the major fragments for an aromatic depends on whether there's stuff attached to it or not. So here's benzyl chloride. And I want to just take a side trip real quick and look at the molecular ion. Because here's our molecular ion at 126. What does this represent? It's 2 peaks away. So we call it an M+2 peak. And notice that since it's 1/3 or about 1/3 the height of the M+ peak, that tells you that chlorine's present. So one of the most logical ways to fragment this particular aromatic, because there's a benzyl carbon there, a benzoic carbon, is I'm going to fragment it there. Why do I want to do that? Because I get a resonance stabilized carbocation. I'll draw it like this. Well, you can pretty much bet that that plus charge is on that primary or that benzoic carbon. And that has a mass of 91. And notice what my base peak is. 91. That's pretty much it. That's all we're going to worry about with this one. And then finally, let's look at bromobenzene here. Again, I want to point out the M+ peak at 156. And then there's an M+2 peak nearly equal in height. That is kind of a dead giveaway that you have bromine present in the compound. Now notice in this case, we don't have any benzoic carbons on bromobenzene. So the logical way to fragment the compound is just break it off at whatever that group is. Because the fragment that results, this benzene cation, has a mass of 77. And notice what my base peak here at 77 represents this benzene cation. And if I were to take the difference between 77 and 156, that would be the mass of bromine. So going from 156 to 77 represents that loss of bromine. So again, just to highlight, you'll have to do some basic interpretation of mass spec. You'll need to know how to find your molecular ion, how to find the base peak. At the very minimum, be able to draw a possible fragment of what that base peak looks like, and maybe one or two other big peaks. But that's where these common fragmentation patterns come into play.